Hey, AP Chemistry. Welcome to part 3 of chapter 8. We're going to talk about more things bonding. And here's a fun fact. We're going to get into a lot more doing today. So let's just jump in. First of all, we ended last video with some pre-thought about naming systems. So we actually have quite a few naming systems. Hopefully you thought through some of those and a lot of it just came back to you. We're not really introducing anything new, but we're going to use the naming systems like till a ghost is given up. A lot. So you really need to know these naming systems inside and out. These naming systems should not be what causes you to pause and think on an exam. We really want to get to the point where it just comes naturally to us to talk about these things and to say the compound names and the ion names and all that good stuff. So let's refresh this. And then what I want you to do with this information is I want you to go practice it. So if you feel like some of this is clunky or bulky or you're not super confident in it, go find some extra practice until this kind of comes naturally and it just flows. Okay, so let's go through it. First of all, we have ions. Our first naming system is really just naming the ions. So remember, that is divided into cations and anions. And the cations just have the element name plus the word ion tacked on to the end of it. So like Ca2 plus is just going to be the calcium ion. Anions, on the other hand, are a little bit different. They have the element name with IDE tacked onto the end plus the word ion. So something like F minus, instead of being the fluorine ion, the end of fluorine is going to be taken off and replaced with ide. So it's now the fluoride ion, oxide ion, nitride ion. Okay, also remember there is a third category here, and that's the polyatomics. A lot of these end in ate or ite. And those that end in ate and ite have a pattern. So they come in a family, and the family has to do with changing the number of oxygen atoms. And changing the number of oxygen atoms is not going to change the charge. So remember, if you have your ate form, one less oxygen is going to be the ite form. One more oxygen is going to be the per ate form. And then if you go two less oxygens from the ate form, you're going to get a hypoite form. So like we can look at nitrate, for example. Nitrate is NO3 minus. If we add an oxygen, NO4 minus, that would be the pernitrate. If we take an oxygen away, NO2 minus, that would be nitrite. If we take two oxygens away, NO minus, that's going to be the hyponitrite ion. So it all hinges on the ate form. You really have to know those ate forms. So if you just kind of skip everything else and just memorize the ate forms, that's usually the way to go. There's a couple in there that don't end in ate. They end in ide, like cyanide is one of those. Also, notice if a sulfur gets thrown onto the front, the ion tends to gain a thio. So like thiocyanide would be SCN. What else do they do? Oh, sometimes they throw a hydrogen on the front. So like if we start with SO4 2 minus, which is sulfate, if they add a hydrogen, it's SO4 minus. Notice adding a hydrogen does change the charge, unlike adding the oxygen on the other side of the page, which does not change the charge. If you add a hydrogen, you either have to throw a hydrogen in front of it, so hydrogen sulfate, or you throw a bi in front of it, bisulfate. And then I think the only other ones, peroxide also ends in ide, similar to cyanide. Ammonium is one of the only cation polyatomics. Polycation. I don't really know where that would go, but it ends in IUM. So those polyatomics are going to come back as well. So once we know how to name the ions, then naming ionic compounds really becomes simple. When you name an ionic compound, all you have to do is name the ions inside. So like if you have NaCl, we name the sodium ion, we name the chloride ion, and the name becomes sodium chloride. You just take the names of the ions, smush them together. Same thing with like Na2SO4. You name the sodium ion, you name the sulfate ion, sodium sulfate becomes the name. Notice in ionic compounds, there's no prefixes that indicate the number of each ion because we can figure it out from the charges. Naming covalent compounds would be our third system. And naming covalent compounds, you don't have to know the names of anything except for the elements and also the prefixes, which indicate the number of things present. So like N2O5, you're going to say the prefix, which shows you the number of nitrogen atoms, then the name of the element. The prefix, which shows you the number of oxygen atoms, and then the element. And then we always end them in ide. Okay, so this would be dinitrogen pentaoxide. So you got to know those prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Nobody cares about 11. Dodeca is 12. And then I think it gets a little bit weird after that. So those are the ones you have to know. And then there are a couple exceptions that happen with naming. And these are from your ionic naming POGL from last year. So if you really want to go deep in it again, reviewing that POGL would be a good idea, but I'll just give them to you here. A, if the first atom has only one, you drop the mono. So like CO2 is not monocarbon dioxide because there's only one of the first atom, so we drop the mono. It's just carbon dioxide. That's the first thing. Second thing is if you get a double vowel, one of the vowels usually gets dropped unless your double vowel is a double I, and in that case we like those for some reason, like skiing. Maybe it just sounds more fun. But spelling really doesn't matter. If you ballpark it and get pretty close, they're going to give it to you on the exam. Also, they don't really test you on nomenclature. They just kind of expect that you're going to come in knowing it. And so that's a nice thing because you don't really have to know the exceptions in and out, but you do have to be able to read the words and pull kind of compounds out of it. All right, naming system number 4 is going to be acids. Remember, there's 2 types of acids. There's the monatomic, mostly monatomic, also known as the ones that end in ide. And then there's the mostly polyatomic ones, also known as the ones that end in ate and ite. And when you change these, ide becomes hydroic. Notice it's not hypo, like the polyatomic ion name. It's hydro. And then ate becomes ic. Ite becomes us. And that's about all you have to know about acids. The only thing is if it comes with a prefix, you want to you want to keep the prefix. So for example, if you're using NO4 minus and you turn that into an acid, HNO4, NO4 minus is pernitrate. So you want to keep that per. So it'd be pernitric acid. An example of the us ending would be like NO2 minus is nitrite. So if you turn that into an acid, it would be nitrous acid. And then a couple examples from the hydroic side of things would be like F minus is the fluoride ion, so HF would be hydrofluoric acid. Same thing with CN minus, that's cyanide. If you turn that into an acid, HCN, it would be cyanic, hydrocyanic acid. All right. I don't know if bases really count as a nomenclature system because bases don't get their own nomenclature system. Bases just take on whatever the ionic naming system because they're really ionic compounds, right? Like NaOH, MgOH2. They just get named as ions. So it's going to be sodium and hydroxide ions inside. So sodium hydroxide for the first one. And then same thing, the magnesium ion is inside that. The hydroxide ion is inside that. So it's just magnesium hydroxide. You just have to remember not to indicate the two because it is an ionic compound and ionic compounds don't get prefixes for the number of each ion we have because we can figure them out. The only other naming system that we talked about is organic. So that would be a good one to go review at this point in time. Remember, there's really 3 parts of naming an organic compound, or at least there's 3 parts that we talked about. One would be the number of carbons, and those get indicated by meth, eth, prop, but, pent, hex, hept, oct, non, dec. Nobody cares about 11, dodec. The second thing you want to name is the bond. So ane for a single bond, ene for a double, ine for a triple. And then the third thing is the functional groups that get tacked onto the end. And now that we're kind of halfway through the year, really, you've seen some of the functional groups that come up over and over and over. And really the ones that we deal with a lot are alcohols and carboxylic acids, right? So definitely know those. Okay, other than that, that's basically what you have to be able to name. There are naming systems out there that we haven't covered. If you look at an ingredient list, you will see that. An ingredient list on any package is going to contain a bunch of compounds that are named in scientific ways. Oh, except for this one, apparently. Way to go, Blue Diamond. You're looking awfully natural these days. But you'll notice that they're definitely in some type of naming system, but it's not one that we've talked about. So there are other naming systems out there. We're not going to deal with them. We are in organic chemistry, and that's about as far as we're going to go. Another note is there can be overlap in naming. Notice these two down here. If you chart them on your type of bond triangle, you'll notice that they are kind of in between. Like they really could be ionic compounds. They really could be covalent compounds too. And what you'll see, even if you look at ingredient lists that contain these things, they get named both ways. So it's really dependent on the industry that they're in. In some industries, it's convenient to treat them like an ionic compound. In some industries, it's convenient to treat them like a covalent compound. So they really get treated both ways. All right, boom, naming. How long did that take us in chemistry? Like 2 months? We go through things a little bit faster these days. All right. Lewis structures. So welcome to Lewis structures. We talked about these a little bit in chemistry as well. Hopefully this will be a little bit of review for you as well, but we are going to go through this and really make sure that we're comfortable with Lewis structures. I like to call them Lewis structures because I was educated in the 90s, but they have very recently changed the name. And so if they ask you to draw one of these, they may call them localized electron models. And it's because in the models, the electrons have a very specific place to be. The electrons are localized, right? They're either in between two atoms or they are delocalized, which means they are outside of that bonding area. And in some cases that will look like they can actually shift around a little bit. So if you hear the term delocalized electron model, they really are talking about Lewis structures. So in some things, these are very simple and straightforward to do. For example, if you look at methane, which is a classic example, right? And you look at the atomic Lewis structures for each of these. So carbon has 4 electrons and hydrogen has 1. It's really easy to see how these come together, right? One hydrogen is going to share with 1 carbon. And so that's going to turn it into a carbon-hydrogen bond. And that actually happens all the way around the atom, right? And so it's easy to see the structure that comes out of that. This would be the Lewis structure for methane. And we really can build that off of the atomic Lewis structures, but some of them are not that easy to see. And that's because the very nature of a covalent compound is that they take the electrons and they donate them to the common good, right? They're kind of a cooperative society. They're kind of a co-op where they take all the electrons and they just distribute them where they need them. And so if, you're dealing with all of these electrons that get distributed in places where they didn't start, you really can't do Lewis structures like I just showed you with the methane. So we have to learn this new method. And the purpose of this method is really to figure out the best way to distribute the electrons around the atom. So let's walk through this and then we'll do a couple examples together. In these notes, we'll do a couple examples together in class, live, and hopefully you'll walk away being really comfortable with this. The good news for Lewis structure is, before we start, it kind of sounds like a lot in the beginning, but as you practice these, if you go through the ones that we do together in the book, you go through your homework, you look up a couple practice things online, what you're going to see is they're all the same. If you look up Lewis structure practice worksheets, they're all the same. There's really only so many examples that work. And so there's really only so many examples that you're going to see. If you do all this practice, you will probably see every single possible Lewis structure that you could see on the exam. So it's kind of nice because it's not this infinite world of possibilities. So if you feel like these rules are a lot, just work through a couple practice, ask your questions, and you're going to feel comfortable really soon. So here are the rules. Rule number 1, you're going to sum the valence electrons from all the atoms. Remember, only the valence electrons are involved in bonding. The core electrons are not. So we definitely just ignore the core electrons. The next thing is you're going to write all the symbols and you're going to attach them all with a single bond. Now, this, first of all, in doing this step, you have to decide which one's going to be your central atom. The central atom is often written first. So there's a little indication in the molecule itself, in the formula itself, as to how they are connected. The other thing is they write them in order of connectivity. So if you notice something like CH3OH, is written with the H's spread out, and that's because they're indicating something to you about what the H's are connected to. These H's are all connected to the carbon. This H is connected to the hydrogen. So the way a formula is written often indicates connectivity. The central atom, getting back to this idea of the central atom, the thing that's in the middle, notice like the carbon, it's going to have to share everything. So the one that you want in the middle is going to be something with low electronegativity, something that doesn't mind sharing. The things with high electronegativity are very grabby. Like they don't want to share. They want the electrons all to themselves. Even in covalent molecules, they're going to work to pull the electrons close to themselves and make them themselves partially negative. So high electronegative atoms are never going to be your central atoms. You want to go low electronegativity. And that's actually how formulas are written also. They're written in order of electronegativity, which is why the central atom, which has to be low in electronegativity, often gets written first. When in doubt, if carbon's involved, make it carbon. Carbon's always the central atom. Carbon is like, it's even on that line in between metals and nonmetals. It's got this like interesting shape, interesting size, interesting electronegativity, which makes it this sharing powerhouse. And it gets an entire name, an entire chemistry class named after it. Organic chemistry is dedicated and devoted to carbon-based compounds. And so it is an extreme sharer. It's if carbon is involved, make it your central atom. Along the same note, never make hydrogen or helium the central atom, because hydrogen and helium can't have more than one thing attached to it. It only has one energy level, and that first energy level can only hold 2 electrons. So hydrogen and helium can't stabilize more than 2 electrons. And notice, as soon as it's sharing with something, it automatically has 2 electrons. So hydrogen and helium, never your central. Carbon, almost always your central atom, if not low electronegativity or the thing that's written first. All right, after you have connected everything with a single bond and determined which one's going to be your central atom, the next thing you want to do is you want to complete the octets of atoms bonded to the central atom. This also known as distribute electrons in pairs to things that need it. You're not going to distribute single electrons. You're going to distribute pairs of electrons. So you want to start from the outside of the molecule in and distribute pairs of electrons to anyone who doesn't already have 8. Okay, at this point in time, you may be done. You want to go ahead and count up how many electrons you started with, how many you used, and see if you are done distributing electrons or not. If everyone has 8 electrons at this point in time, if everyone has an octet, your Lewis structure is done. Now, there's a couple cases where your Lewis structure is not going to be done. And here are the 2 cases. First of all, if everyone has an octet and you have extra electrons, then you're going to place any leftovers on the central atom. Now, this leads us to an exception to the Lewis structure, and we'll talk about that in just a second. Let's get through the non-exceptions first, and then we'll talk about this specific case as an exception. The other option, so if this is option A, option B, I guess if option C is you're done, maybe we should have made that option A. Oh well. Okay, option B would be you've distributed all your electrons and not everyone has an octet. Someone still needs electrons. In this case, you're going to try multiple bonds. And again, I'll show you an example of this and I'll show you why it works. So let's try some of these together using this set of rules. No notes, go away. Okay, We'll start with an easy one. Let's start with H2O. So with water, we're going to walk through these steps. Step number 1, tally up all our valence electrons. So we have 2 hydrogens, and each hydrogen has 1 valence electron. We have 1 oxygen, and each oxygen has what? 6? Okay, so we have 8 electrons total to distribute on this molecule. Number 2, we're going to choose a central atom and attach everything to it with single bonds. So looking at this, our options are hydrogen and oxygen. Hydrogen can never be the central atom. It has to be oxygen. So we're going to draw oxygen and attach everything to it with single bonds. Now, it doesn't have to be symmetrical, but usually if you make it as symmetrical as possible in all the following steps, it's going to work out better. You're going to have to do less adjusting at the end. Number 3, we're going to tally up the electrons that we have used and what we have left over. We're going to distribute them in pairs to things that still need electrons. So we've used 1, 2, 3, 4 electrons. We have 4 left. So we're going to distribute them to things that still need them. Now, if we look, hydrogen is associated with 2 electrons already. Hydrogen is fine. Hydrogen doesn't need any more electrons. But oxygen, on the other hand, oxygen has only 4 electrons. So oxygen still needs electrons. So we're going to distribute them in pairs around oxygen. Again, you don't have to do it symmetrically, but the more symmetric you make it, the less you have to adjust later. I used 4. Okay. Now, here are my 3 options. I'm out of electrons. I'm either done, I have extra electrons, or somebody doesn't have enough electrons. So which case is it? Hydrogen has 2, hydrogen has 2, oxygen has 8. I am out of electrons. Everyone has a complete octet or duet. So I'm done. This minus the yellow circles. I don't know if I can erase them completely. I'll just erase them as much as I can. Okay, this minus the yellow is my localized electron model. Ta-da! Okay, let's do a couple more for practice. Now would be a good time to pause the video and work these out at the bottom and see how they go. All right, HF. I have 1 plus 7. I have a total of 8. Now this one doesn't need a central atom because I only have 2 atoms. So I just connected them to each other with a single bond. I've used up 2 electrons. I have 6 left. Hydrogen, again, doesn't need anything else. The 2 shared electrons in the bond count as the 2 that hydrogen needs. Fluorine, those 2 in the bond, also count for fluorine. Fluorine only has 2, it needs 8, so I'm going to distribute my remaining electrons in pairs. 1, 2, 3, 4, 5, 6. And now I have no electrons. Hydrogen has a full outer electron shell. Fluorine has an octet. And they're happy. That's my Lewis dot diagram. Let's do elemental nitrogen. Okay, so nitrogen is going to be 5 plus 5. So I have a total of 10 electrons. Okay, again, I'm not going to have a central atom because I only have 2. Connect them with a single bond, subtract off the electrons used in that single bond. I have 8 left. Okay, so both nitrogens need them. I'm going to distribute them. 1, 2, 3, 4, 5, 6, 7, 8. So I am out of electrons. Does everyone have a full octet? No, it does not. So now what do? I can't invent electrons. If I invent electrons, I would be adding a charge, and there's no charge on this molecule, right? So I have to work with the electrons I do have. So what you're going to do, this is option B. If you have distributed all your electrons and someone still needs an octet, you're going to try multiple bonds. So what we do is we take these 2 electrons that are currently belonging to this nitrogen only, we're going to put them in the middle here so that they belong to both nitrogens at the same time. So it's just a more efficient use of electrons. Instead of counting towards one, they now count towards both. So I'm going to do that. I'm going to take these electrons off of this nitrogen and I'm going to share them. Okay. So the nitrogen here on the left now has 8, but the nitrogen here on the right that so sacrificially gave of its precious electrons does not have 8. It still only has 6. So the other nitrogen has to step up and do the same thing. So we're going to take electrons off of this nitrogen on the left. We're going to put them in the middle. And I'm drawing them as dots. So you can see that I removed 2 and I put 2 in the middle. But you can draw them as lines also. Okay, so I still have only used 10 electrons, 2, 4, 6, 8, 10. Okay, but now both nitrogens have an octet. Look at this. So 8 for this nitrogen, 8 for this nitrogen. Everyone has 8. Everyone's happy. I've used up all my electrons. And I now have a completed Lewis structure, okay? So that's what it looks like to use multiple bonds. You just have to recognize that you're out of electrons and something still doesn't have an octet. A word of caution on multiple bonds. Don't start with them. Don't try multiple bonds until you run out of electrons. It's possible to make structures that complete octets and use up all the electrons with multiple bonds where the multiple bonds don't actually exist. You have to run out of electrons before you try multiple bonds. Okay, now I'm going to say that, and you're going to repeat it to yourself, and you're going to write it in your notes, and someone is still going to try it. So this is why we do practice, right? To get all the kinks worked out. But hopefully you remember that. Don't try multiple bonds until you run out of electrons first. All right. NH3, we can go through these more quickly. NH3 is pretty straightforward. So I have 5. Each of my 3 hydrogens has 1. I have 8. So everything's going to be connected to nitrogen with a single bond. I just used 6. I have 2 left. None of the hydrogens need those 2, so they get put on nitrogen. I am out of electrons. Hydrogen, hydrogen, hydrogen all have their duet. Nitrogen has its octet. That's my Lewis structure. All right, last one, NO+. Now, this one, nitrogen has 5, oxygen has 6, but it has a plus sign. So anytime you're dealing with an ion, you need to respect the charge by either adding or subtracting the electrons that have been added or subtracted off this compound. So positive charge means we lost negative electrons. So I'm going to subtract 1. I am working with 10 electrons here. So nitrogen gets attached to oxygen with a single bond. I just used 2. I have 8 left. I'm going to distribute those 8 in pairs until I have none left. They both still need electrons. I'll take off a pair and make it share. Oxygen is happy, nitrogen is not. So I'm going to take off another pair and make it share. And that is my Lewis structure. All right. Okay, so as far as like a standard localized electron model goes, that's the gist of it. There's a lot of practice in your book. Definitely go through that practice until you feel comfortable with it, and bring me questions that you have. Now let's go through the exceptions. So, of course, there's exceptions to our model, of course. And there's 2 ways you can have an exception. You can have a structure that has atoms with more than an octet, and you can have a structure with atoms that have less of an octet. So let's kind of go through the parameters here. So and I guess there's exceptions where the model has an odd number of electrons. That is possible. You really need a more sophisticated model in order to deal with this, which is why that exception didn't even pop into my head when I saw the word exception, because it really doesn't show up on the AP test. So fair warning, it does exist. You can see some examples here. You really need a more sophisticated model than the localized electron model to deal with it. And so in our own model, if you run into these, you just leave something with one electron, and it looks funny, and it is funny. It indicates a really high state of potential energy. It's going to indicate a really reactive compound, and we're not going to deal with it. So that's exception number one. Exception number two is where an atom has less than an octet. So in this case, it has to be an atom that really is low in electronegativity. And it has to be small enough so the electrons it does have are stabilized. And so it really comes down to two atoms that do this, beryllium and boron. Those are the only two atoms you're going to see that ever form something with less than an octet. Now, the tricky thing about these is that if you draw a molecule, a Lewis structure, it is possible to take your current structure and draw a legal Lewis structure. So check this out. So if we have BF3, we have how many for boron? 3 for boron, and then 3 times 7 for fluorine, so 21, 24. We have 24 total electrons. You're going to connect them all to boron because it's the least electronegative element. We've used 6. We have 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Now, if this were any other molecule, what we would do here is we would recognize that boron is electron deficient, and we'd take one of these fluorine shared things and electron pairs, and we'd move it into the bonding. So notice we can end up with a legal Lewis structure, which would look like this. But we don't. And we're going to talk about a scenario where you end up with two possible Lewis structures and you have to decide which one is the best. And we do have a method of solving that. It's called formal charges, and we'll talk about that here in a couple slides. But for now, just know that this is the actual formula. Before you move that over and form that double bond, boron and beryllium both can form stable compounds where boron and beryllium are electron deficient. Now, it is a stable compound. However, it's also a reactive compound. And so that compound is going to react fairly quickly with anything that's electron heavy, with anything that has a negative charge or extra electrons on it, like ammonia. If we look at ammonia, that nitrogen is holding a lone pair. So just the fact that the nitrogen is holding a lone pair are going to make these two compounds react quickly together. So it is a stable compound. It is considered the best localized electron model, but it's also a reactive compound. Okay, so that's your second exception, I guess, or the first exception you're actually going to have to deal with in our curriculum. The second one is a molecule that has atoms that are holding more than an octet. Okay, now only certain atoms can do this also, and the catch here is you have to have a D shell available. So notice that nothing in the first or second energy levels is going to be able to do this because the first energy level just has the 1s shape. The second energy level has 2s and 2p. Neither one have a D shell available until you get to 3. 3D is the first D shell we see available. So anything that holds an expanded octet is going to have to be in the third energy row or below. Or the third energy level or higher. You could say it either way. Now, practically, we don't see too many things doing this. Phosphorus and sulfur are very common. Some of the halogens also do this on occasion. But again, as you're looking for practice on this, you're going to start seeing the same examples over and over and over, which is kind of nice. Because then you get very used to those and you start to recognize them and you feel very comfortable with them. We'll go through examples for both of these. Okay, so here's BF3. We definitely already did this. And you end up with boron electron deficient. Another example would be BH3. We can do that one. So boron would have 3. We have 3 hydrogens. Each of them have 1 valence electron. So you end up with 6. So you connect them all to boron. And actually, in this case, we can't write a second thing that works. But boron, because it's not very electronegative, is going to be very stable like this. And this is the Lewis structure. All right, let's do SF6. SF6. So sulfur has 6 valence electrons. We have 6 fluorines. They all have 7. Holy smokes. Okay, so that's going to be a lot of electrons. All right, 6 times 7 is 42. It's basically 6 times 8. Okay, 48 electrons. So here we go. S, F, 1, 2, 3, 4, 5, 6. Oh my goodness. 1, 2, 3, 2, 4, 6, 8, 10, 12. So 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 times 2, 36. Okay, so in this case, notice that sulfur is the central atom and sulfur is holding the additional load. Sulfur is holding the expanded octet. And that's always the case. If you have something with an expanded octet, it's always going to be the central atom. In this case, the sulfur is holding 2 extra bonds. You'll see some cases where, you'll have some things bonded on and then you have electrons left over and those electrons just get added as lone pairs to the central atom, but always the central atom. The exterior atoms cannot hold extra electrons. The one in the middle can because it's already sharing what it has. It doesn't truly have 8. It's sharing 8. It has part of 8. So once in a while, that central atom can stabilize a couple extra electrons. Okay, so we'll get into some practice with that together. And then next time, we'll get into a couple more details about the localized electron model, like formal charge and resonance. And then we'll be moving right along. So let me know if you have questions. I will see you in class.